right, welcome back. So in this tutorial, we're going to do our final segment where we're going to look at building our first neural network for binary classification using TensorFlow and Keras. So for the most part, this is a continuation of the previous video. If you haven't watched the previous videos, I would highly recommend to go ahead and check them out, where for the most part we were mainly looking at how you can actually go ahead and sanitize your data, doing all the fun things before you start training your model. So for the most part, we dealt with loading our data set, where we load data that we got from Cargo, and we also did a little bit of visualization of our data, because before you start training any model, it's very, very important to actually go ahead and visualize your data. And so for the most part, we did a bit of visualization where we are looking at each and every category that we have, both numerical and categorical data that we had in our training set. So for the most part, we looked at how you can actually go ahead and visualize this data, so that you can sort of like know what your model sort of like should build towards. So it's very important to always visualize your data. Then we also looked at how you can actually go ahead and clean your data set, where you can drop columns that are now in your test and validation data set. Then we also went ahead and looked at extracting labels, where you can actually go ahead and extract your labels in this case, which is basically your training data. And we did a bit of feature engineering, where we needed to sort of like handle categorical data and numerical data. So there are quite a number of concepts that we looked at, including one-hot encoding, label encoding, and hashing as well. So I highly recommend to actually go ahead and check out the previous videos before you jump into this one. But for the most part, if you are comfortable in cleaning your data set, extracting training, validation, and test sets, and you are familiar with that concepts, you can actually go ahead and start from this video. So in this case, we are going to build our first deep neural network for binary classification, where this is a continuation of our model. So what we want to build basically, since our input data is a vector, which is basically a 2D tensor for the most part, and our labels are scalars, which is 1 and zeros, which is a 1D tensor. This is sort of like a good sort of like scenario that you can ever encounter. So one of the typical, so I'm just reading these notes anyway, one of the typical network that can perform well in such a condition is you can build a fully dense connected layers with ReLU as our activation function, right? So in this case, ReLU is going to act as our linear rectifier, which is meant to zero out all negative values, and sigmoid is going to squash all arbitrary numbers, right? So we have talked about this in the previous videos, so if you haven't watched them, I highly recommend to actually go ahead and check them out. So without further ado, let's simply go ahead and start building our first neural network. All right, so to build our first deep neural network, we need to be using Keras from Keras import models, right? Then we also need to import layers. Remember, whenever we are building our deep neural network, there are a couple of layers that we need to be able to sort of like configure in order to build our deep neural network. Then the third import, I need to import an optimizers, right? So once we have imported this, let's now build, let's just go ahead and run it, right? So let's now build our first sequential model, right? So in this case, we're going to be using a sequential model because it allows us to build these layers, right, for a neural network. So let's simply go ahead and say model. So this is going to be my model. It's going to be models dot sequential, right? And then in this case, I'm simply going to use the layers to access our layers, right? So in this case, like what I've mentioned before, for our layers, we're going to be using some dense layers, right? So we're going to build a fully connected dense layer kind of model. So in this case, I'm going to simply say dense 16, right? And then for our activation, in this case, we're going to use relu, right, as our activation function. Then for my input shape, I need to be able to tell my Keras that my input shape is going to look like this. So in this case, for my data, I'm simply going to take the train data set. So remember, we had the X train, and then I'm simply going to take the shape of that, and that's what I'm going to pass here. Okay, so this is our first layer. All right. So let's build our second layer. So for our second layer, we are going to use again a dense layer of 16 units. And then the activation function is going to be relu again, right? So in the second layer, we don't necessarily need to pass the input shape. This is because Keras will automatically infer it, right? So we don't need to pass a layer here, right? So these two layers will do just fine. Since we are doing a binary classification, we now need we need to tell Keras, our output layer, what it's going to look like. So in this case, since we are doing binary classification of either 1 or 0, we're going to do a unit of 1. And then our activation function in this case is going to be sigmoid, right? So in this case, you have to take note, the activation function has changed. It's no longer relu because we are now dealing with the final result, which is going to be computed at a arbitrary sort of like a small space as compared to the relu ones, which was looking at the greater perspective. So in this case, we're simply going to use sigmoid since we're doing binary classification. So once you have done this, this is basically our deep neural network for binary classification. You can simply go ahead and compile, right? So in this case, our model is compiled. Of course, it has a warning, which is fine. We can ignore this for now. But for the most part, our model has successfully compiled, right? So the next thing that we need to do after the model is compiled is we can actually go ahead and check the summary of our model, right? So in this case, we can actually see that this is the summary of our model. In this case, you can see that we have 3 layers that we're going to use to build our deep neural network, and the output shapes are there, including the last layer, which is going to be which you said is sigmoid, which is going to do binary classification with 1. And it can actually tell you the total parameters, the trainable data. So we have 545 parameters, and the training data is also 545, and the non-trainable parameters in this case is 0, right? So once we have built our model, the next step that we simply need to look at is basically compiling the model, right? So to compile the model, I'm simply going to write another heading here called compile the model, right? Oh, so is this not a markdown? I need a space here. All right, so to compile the model, I'm simply going to say model.compile. So we have built the model. So on compilation, this is where we define our loss function, the optimizers, and the accuracy, right? Like what we've discussed in the previous videos. So in this case, I'm simply going to pass an optimizer, right? So I'm simply going to say optimizer. So in this case, the optimizer that I'm going to use, since we're going to do binary classification, one of the optimizers that works well is the RMS op, right? So there are quite a number of optimizers, so you can try them out, but in this case, I'm going to use this. And then for the loss function, I'm going to do binary cross entropy, right? And then the third argument that I'm going to define is basically the matrix. So for the matrix, I'm simply going to say matrix. In this case, we want to train our model using the accuracy function. So in this case, I'm simply going to want to be able to view the accuracy in terms of how our model is doing, right? So remember, let me just recap this. We said our loss function, basically, it is simply an algorithm that does checks how our model is predicting, right? Because remember, we have our outcomes, which are our labels. So we know exactly. So as you are training the model, we are taking the input data, comparing against the model, and see how our model is doing for the most part, basically, during training. So this is sort of like a prediction against the true target, you know, and then we can see how the model is doing. That's how the loss function work, right? And then the optimizer, for the most part, an optimizer, like what we mentioned earlier on, it implements what we call a back propagation algorithm, right? Which takes what we call a loss score that will be calculated by this as a feedback to the layers, right, to adjust the weights. So the idea of this is the optimizer is it says, okay, hey, according to the loss function, this is the loss score that I've been given. Then according to the layers that I'm passing here, for example, the first dense layer of 16 units, another one of 16, it sort of like takes the value and then put them back as input, right? So the idea is once it's put them as input, the idea is sort of like to tweak them in a way or in a direction that will sort of like lower the loss score. Because the idea is the model will try by all means to reduce the loss score so that it improves the accuracy. So we have mentioned this in the previous videos, so you can actually go ahead and check them out. So in this case, I think I'm happy with this for now. So let's just go ahead and compile. Okay. So once you have compiled our model, it means our model is working just fine. So the last step, we now need to train our model. So to train my model, I'm simply going to say to introduce. So to train the model, in this case, since we're doing binary classification through trial and error, I've seen that 15 epochs will work. And then I'll introduce a batch size. History is equals to model fit, right? So you say model.fit. In this case, then we now need to pass our training data set. Then our Y train data, right, which is basically our labels, right? And then in terms of the number of epochs, I'm going to say 15 for now, or 10 will do. Then a batch size, I'm simply going to be passing a batch of 32 as I'm passing this, right? So since we want to know how our model is doing during training, I'm simply going to pass our validation data that we have already extracted, right? So for our validation data, we had the X validation for our input data set, and then our labels as the output. These are the labels, right? Sorry, so this is not actually X train. So this is X validation, right? So remember we had extracted the the validation data, because whenever you are training your model, we should never train it with data that it is already seen. So in the previous video, we separated the training data and the validation data, right? So this is what we are simply passing here. So to compile or to train the model, we simply press play in this case, right? So as you can see, my model is now training. So the idea is, what we want to see is, first of all, we want to see the loss being decreased. So for example, we start at 0.3 and it's actually reducing, right? And then the accuracy is started at 0.4 and we're increasing. Same as the validation accuracy, we need it to increase as well. Then the validation loss, right, we also need it to decrease. So as you can see, the model has done fair in this case, up to 90% of validation accuracy. Then, oh sorry, of the training accuracy using the training data. Then the validation accuracy in this case is around 89%, which is almost similar training accuracy. Then the loss is fairly fine. All right, now it's probably time to visualize our data. So for our data, what we're going to do is we're going to use the history function. So for example, if I say the history is basically the trained model, which I've saved to a variable called history. So if I say history.history, you can actually see that we are getting some information in terms of the accuracy data for the 15 epochs. Yep, for the 15 epochs that we train the data. So we have basically this. So it's showing us the accuracy, the loss, the validation accuracy, and the validation loss, right? So this is basically this array here. So it's a JSON object that has an array of arrays. So for example, under the key accuracy, it has this array, then loss, then the other ones are hidden, but it's basically loss, validation accuracy, and validation loss. So we just want to visualize this so that we can see some sort of like the behavior in terms of how our model has performed. So in this case, I'm simply going to plot this with matplotlib. So I'm simply going to import matplotlib, right? Then pyplot as plot, right? And then I'm simply going to create a function, right? So the function that I'm going to create is going to be called plot graphs, where I'm simply going to pass the history and then the name, right? Or the string or the label rather of the specific key in our history data frame. So in this case, I'm simply going to say plot. I'm going to plot like this, right? So in this case, I'm going to say so history.history, right? And then I'll pass the string here. So I'm just going to make this as a function where the user will simply pass. So for example, let me just demonstrate this. So for example, if I say plot graph, and then I'm going to pass the history object, which is my trained model, and then I'm going to pass the key called accuracy. Right, so this is what we're seeing right now. So this is the accuracy sort of like graph, right, which is sort of like increasing in accuracy, as we have already seen in the output of our model as it was being trained, right? So we need to do the same for the validation. So for the validation, I'm simply going to pass, since it's called validation accuracy, I'm simply going to instantiate a key called val. I can say underscore here, then I say concatenate like this, because it's going to be called validation accuracy, like so. So I'll simply pass this. So again, if I plot this, we now have a validation accuracy here, right? So I'm simply going to do the same for the rest of for the valid for the loss as well. So there are a couple of things that I need to do actually. So let me just plot the loss anyway. So the loss will look like this. So the loss will also do the same thing. It will have a validation loss and loss, right? So right now it's being plotted on the same graph, which I want to separate these two. So let me just add a few lines of code that will basically label our x-axis, our y-axis, and then draw this as a legend and then show this graph like so. So this is sort of like separate our two graphs like so, right? So what's going on, right? So in this case, we can actually see that if we check our validation accuracy graph, right? For our trained data, it actually did well up to 90%, right? And you can see a smooth curve climbing. So ideally for a perfect model, this blue line should climb up to 100%. So you should see a smooth curve up to 100%. And for our validation accuracy, we should also see a similar pattern where this was supposed to start maybe there and then climb until there, right? But in this case, we can see that our validation accuracy, the graph is going down after epoch. After the first epoch, actually, the graph is now decreasing, which means it's now losing accuracy after the first epoch, and then it goes up, down, up and down. So also on the validation loss, we can see the loss was decreased, which means as our training data, the loss was actually decreasing. But for the validation loss, it decreased. But after epoch number 7, somewhere here, right, it started going up again and then down, up. So what we are seeing here is basically a classic overfitting issue, which we can rather solve in this case. So overfitting, it usually happens when you are sort of like over optimizing. So in this case, we can actually see that we have had 15 epochs, which might be a lot, right, for our training and test dataset. So 15 epochs or 15 layers might be a lot. So we might need to reduce that. That might solve our overfitting issue. Also, maybe our model, the way we architected here, when we compiled, maybe this might not be the best compilation that we did here in terms of we need to specifically pass the accuracy so that it will be a little bit lower. So what I'm going to do for my first attempt, right, I'm simply going to comment this for now, right? So I'm going to comment this, and then I'm going to declare another, I'm going to recompile this model again, right? So the way I'm going to compile it this time, so let's just build the model, right? Then summary. Then the way I'm going to compile this time, I'm going to explicitly pass the optimizer. So instead of saying RSM prop, I'm simply going to use the RSM prop as a class where I can pass the learning rate. So in this case, the learning rate, I'm saying I want you to learn at a 0.001 sort of like rate or percent. And then the loss function, I'm going to use the binary close entropy. So I'm just going to try this version of this model and see if it somewhat improves our model. So in this case, our model is failing to compile for some reason. So let's just see. Okay, so this is okay, metrics are okay, optimizer is fine. So let me simply redeclare this model.summary and model.compile. Okay, so there is something wrong. The argument learning rate is no longer recognized. So it looks like this thing can no longer take the learning rate anymore, which can be fixed. So let me not pass RL, let me just pass the learning rate. Okay, so maybe I have a newer version of, I did reset my laptop at some point. So anyway, so the learning rate, I don't need to explicitly pass LR anymore, maybe from this new TensorFlow. Simply need to pass as a value like this. So it has compiled. Then let's train it again. Right? So right now I'm still training it with 15 epochs. Let's see if this will improve our model. For our test accuracy for the training data is still getting up to 90%. And this is at 9. It looks like there is no much change. Let's plot the graphs. Yeah, so there isn't much change from this. Actually, after the first epoch, it's now decreasing in accuracy again. But this one is a bit better. So So this one, it decreased after the second epoch actually. So let's try to retrain again. So instead of 15, let's train it with 10 epochs for now, right? So instead of 15, let's just use just 10 epochs, right? Because one of the issues that causes overfitting here is you can actually see that after the first epoch, right, the model is starting to overfit, right? Which in this case it means we are sort of like over optimizing on the training data, right? Which is an issue, which means our model will not generalize well on the data that it hasn't seen before. So right now we have done with 10. Let's see if there's an improvement. So let's plot the graphs. Yeah, this is now even worse. Yeah, this is now worse. Yeah, this is worse. So actually let me just clear all this and restart, because sometimes it's sort of like it starts to memorize these things if we continue running it. So I'm simply going to restart again, and then I'll run everything. One of the things that it does is if you keep on compiling the same model, the neural network will sort of like start to memorize. It won't be training anymore. It will start to memorize. All right. So from this one, we can actually see that the model after 10 epochs, the model is now a little bit better as compared to the 15 epochs that we had earlier on, right? So let's investigate. So this one for the validation for the training data, right, is training well up to 91%, which is okay. Then for the validation data, we can actually see that it has improved, right? It's increasing. Our graph is still increasing, but we can see that after maybe the fifth epoch here, after the fifth epoch, our validation data started to lose accuracy, started going down, right? So which means they're still overfitting after the fifth epoch or so. So right now, let's train it up to the fifth epoch. Let's see the behavior here. So here it was decreasing, and after the fifth epoch again, it started increasing, which means the validation loss started increasing again and then decreases. So which means there's a little bit of overfitting here. So let's restart everything again and stop it after just 5 epochs, right? Because our data might not be a lot to do 15 epochs, and it might not be complicated enough to do 15 epochs. So in this case, let's just train it up to 5, right? And then so I would decrease the number of epochs in this case to 5, right? And I'm simply going to clear all outputs, restart everything so that it won't memorize things, and then I'm simply going to say run all, right? So in this case, we now want to see what it would look like after just 5 epochs, right? Yeah, so this is a little bit better, even though we lost accuracy by 1 point, by 0.1. This is now 89. The other one was 90, but the validation accuracy and the training accuracy, they are now equal. So in this case, it's now a little bit better, which means we can use this one for now, right? So what I was just trying to demonstrate here is overfitting can be caused by quite a number of things, right? So overfitting is really a concept that I will cover in the following videos. So just make sure that you stay tuned to the channel so that you'll see when I drop this overfitting concept. So there are a lot of ways where you can handle overfitting. We can do undersampling, you can do oversampling, you can do what you call the SMART sort of like implementation, because the idea is you might have data which is sort of like leaning towards being positive data, or let's say in this case it was a binary classification. Maybe we had more ones than 0, so the data should be sort of like balanced. We should have 50-50 for our training data against our labels. So we should have 50% with the labels that are positive and then 50% negative. That's good data set. But in this case, our data set, I will show you what it looks like. It's not balanced at all. So that's why we are seeing these overfitting problems. But I will cover this. But for the most part, this is how you mainly train a binary classification. So let's simply now do what we call model evaluation. Let's now evaluate our model in terms of how it has performed, right? So I'm simply going to do another heading here called model evaluation, right? So for model evaluation, what I'm simply going to do, I'm simply going to add a block of code. So I'm simply going to say results, right, is equals to a model that we have trained, then dot evaluate. So we want to evaluate basically our numeric test data. So remember, for our test data, we had already created, everything was created as one hot as numeric test data. Then I'll also evaluate the one hot encoded test labels as well, right? And then let's see what this looks like, right? So let's compile this, right? So this is what we have seen, right? So the validation accuracy for our training data was 89%. This is what we've already seen here. And then, so if we're simply to print the results, it should get us the same thing. So if I say results, it should get us this object as an array, right? So you can actually see that our model is generalizing a little bit better with 89, 90% in terms of validation accuracy, which is not bad, but this needs to be improved because binary classification, it should get at least 100%. But because of the data that we had, it was not balanced at all. So just to show you, if I print a histogram of our training labels in this case, right? So if I say training labels dot histogram, so right, so that you can actually see. So you see, this data is not balanced at all, right? So with approaches of handling overfitting, you can oversample the underrepresented. So which means in this case, for the clients that had a bank prediction who took this sort of like what was the original problem, by the way, of our so for the clients who said no in terms of taking this campaign, there are quite a lot as compared to the client that said yes, right? So in this case, you can see we have something like 10% against 90%. So this data is not balanced. That's why you saw we had a lot of overfitting and sampling. But the reason why I did this tutorial using this data set is this is a real world situation that might happen. So in order to resolve this, you need to do sampling. You need to handle these sampling issues by doing SMOT analysis or oversampling the underrepresented. In this case, we can oversample this, which whereby we will create some sort of like virtual data so that this will be almost 50-50 against this. But for now, if your data is balanced, you should see that your model is doing well. So that was it for this tutorial. I hope you have learned something in terms of how you can build our first deep neural network, in this case for binary classification. And I hope you have learned something. So let me know in the comments down below if you found these videos interesting, whereby I was planning to do a little bit of AI. So if you find them interesting, just let me know so that I'll continue publishing these videos. Otherwise, stay tuned and see you in the next one.